Gravity doesn't pull anything, and almost everyone learns it wrong. This isn't some fringe theory or conspiracy. It's not pseudoscience. It's what physicists have known for over a century, but somehow, the way we teach gravity in schools hasn't caught up. We're still using Newton's language from the 1700s, even though Einstein fundamentally rewrote the rules in 1915. Carl Sagan spent decades trying to fix this misunderstanding. Not because he wanted to sound clever, but because getting gravity wrong means getting reality wrong. And once you see it the right way, you can't unsee it. Carl Sagan was an astronomer, a planetary scientist, and one of the greatest science communicators who ever lived. He didn't just study the cosmos, he made it accessible. His television series Cosmos, A Personal Voyage, which aired in 1980, reached over 500 million people across 60 countries. But Sagan wasn't interested in dumbing things down. He was interested in clarity. He believed that the universe was understandable, that science wasn't reserved for specialists, and that the most profound truths could be explained in plain language. Gravity was one of his favorite examples. Because gravity, he argued, isn't what you think it is. It's not a force at all. Let's start with what you were taught. In school, you probably learned that gravity is a force of attraction between two objects with mass. The Earth pulls you down. The sun pulls the Earth. The moon pulls the oceans, creating tides. Isaac Newton described this in 1687 with his law of universal gravitation. Every object attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. It's elegant, it's mathematical, and it works, mostly. Newton's equations can predict planetary orbits, calculate rocket trajectories, and explain why apples fall from trees. For everyday purposes, Newton's gravity is more than good enough. But here's the problem. Newton's gravity doesn't explain how it works. It describes what happens, not why. How does the Earth reach across empty space and pull on you? How does the sun exert a force on planets millions of miles away without touching them? Newton himself was troubled by this. In a letter to Richard Bentley in 1692, he wrote that the idea of gravity acting at a distance through empty space was so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. He knew his equations worked, but he also knew something was missing. That missing piece arrived in 1915, when Albert Einstein published his general theory of relativity. Einstein didn't just refine Newton's ideas. He replaced them entirely. According to Einstein, gravity isn't a force pulling objects together. It's a consequence of the geometry of spacetime. Mass doesn't pull, mass curves, and objects moving through that curved spacetime simply follow the straightest possible paths, called geodesic. You're not being pulled toward the Earth. You're following the shape of space itself. This is the idea that Sagan fought to make clear. Because once you understand it, the entire universe starts making sense in a completely different way. Let's break it down with an analogy, one that Einstein himself used and that Sagan often referenced. Imagine a trampoline stretched tight and flat. Now place a bowling ball in the center. The trampoline surface curves downward around the ball. If you roll a marble near the edge of the trampoline, it doesn't travel in a straight line anymore. It curves toward the. Gravity doesn't pull anything, and almost everyone learns it wrong. This isn't some fringe theory or conspiracy. It's not pseudoscience. It's what physicists have known for over a century, but somehow, the way we teach gravity in schools hasn't caught up. We're still using Newton's language from the 1700s, even though Einstein fundamentally rewrote the rules in 1915. Carl Sagan spent decades trying to fix this misunderstanding. Not because he wanted to sound clever, but because getting gravity wrong means getting reality wrong. And once you see it the right way, you can't unsee it. Carl Sagan was an astronomer, a planetary scientist, and one of the greatest science communicators who ever lived. He didn't just study the cosmos, he made it accessible. His television series Cosmos, a personal voyage, which aired in 1980, reached over 500 million people across 60 countries. But Sagan wasn't interested in dumbing things down. He was interested in clarity. He believed that the universe was understandable, that science wasn't reserved for specialists, and that the most profound truths could be explained in plain language. Gravity was one of his favorite examples. Because gravity, he argued, isn't what you think it is. It's not a force at all. Let's start with what you were taught. In school, you probably learned that gravity is a force of attraction between two objects with mass. The Earth pulls you down. The sun pulls the Earth. The moon pulls the oceans, creating tides. Isaac Newton described this in 1687 with his law of universal gravitation. Every object attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. It's elegant. It's mathematical. And it works, mostly. Newton's equations can predict planetary orbits, calculate rocket trajectories, and explain why apples fall from trees. For everyday purposes, Newton's gravity is more than good enough. But here's the problem. Newton's gravity doesn't explain how it works. It describes what happens, not why. How does the Earth reach across empty space and pull on you? How does the sun exert a force on planets millions of miles away without touching them? Newton himself was troubled by this. In a letter to Richard Bentley in 1692, he wrote that the idea of gravity acting at a distance through empty space was so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. He knew his equations worked, but he also knew something was missing. That missing piece arrived in 1915, when Albert Einstein published his general theory of relativity. Einstein didn't just refine Newton's ideas. He replaced them entirely. According to Einstein, gravity isn't a force pulling objects together. It's a consequence of the geometry of spacetime. Mass doesn't pull. Mass curves. And objects moving through that curved spacetime simply follow the straightest possible paths, called geodesic. You're not being pulled toward the Earth. You're following the shape of space itself. This is the idea that Sagan fought to make clear. Because once you understand it, the entire universe starts making sense in a completely different way. Let's break it down with an analogy, one that Einstein himself used and that Sagan often referenced. Imagine a trampoline stretched tight and flat. Now place a bowling ball in the center. The trampoline surface curves downward around the ball. If you roll a marble near the edge of the trampoline, it doesn't travel in a straight line anymore. It curves toward the. This also explains why objects of different masses fall at the same rate in a vacuum. Drop a feather and a hammer on the moon, as astronaut David Scott did during the Apollo 15 mission in 1971, and they hit the ground at the same time. Newton's explanation was that the gravitational force is proportional to mass, but so is inertia, and they happen to cancel out exactly. It works, but it's a strange coincidence. Einstein's explanation is simpler. Both objects are following the same curved spacetime. There's no force to begin with, so mass doesn't matter. As physicist Richard Feynman put it, the same rule works for everything, and that's the beauty of it. But spacetime curvature doesn't just affect motion through space. It affects time itself. This is one of the most validated and practically important predictions of general relativity. Clocks run slower in stronger gravitational fields, or equivalently, deeper in curved spacetime. A clock on the ground runs slower than a clock in orbit. The Global Positioning System, or GPS, relies on satellites that orbit about 20,000 kilometers above Earth. Those satellites experience weaker gravity than we do on the surface, so their clocks run faster, about 45 microseconds per day faster. If engineers didn't account for this relativistic effect, GPS coordinates would drift by several kilometers every single day. According to physicist Clifford Will, who has extensively tested general relativity, every time you use your phone's GPS, you're proving Einstein right. Sagan loved these kinds of examples because they showed that relativity isn't abstract. It's woven into the tools we use every day. But he also loved the bigger picture. If gravity is geometry, then the universe itself has a shape, and that shape depends on how much mass and energy it contains. Einstein's equations allow for three basic possibilities. The universe could be flat, like an infinite plane. It could be positively curved, like the surface of a sphere, or it could be negatively curved, like a saddle. Current observations, including data from the Wilkinson Microwave Anisotropy Probe and the Planck satellite, suggest that the universe is remarkably flat on large scales, to within about 1%. According to cosmologist Max Tegmark, the universe appears to be Euclidean, at least across the observable portion. Now let's bring this back to Earth, literally. Why do we still teach Newtonian gravity in schools if Einstein's version is more accurate? The answer is practicality. For most everyday situations, Newton's equations are simpler and accurate enough. If you're building a bridge, launching a weather satellite, or calculating the trajectory of a baseball, you don't need general relativity. But the conceptual framework matters. When students are taught that gravity is a force, they're being taught a model that we know is incomplete. They're learning a useful approximation, but they're not learning what gravity is. Sagan argued that we owe students more than that. We owe them the truth, even if the truth is harder to visualize. This is where Sagan's genius as a communicator came through. He didn't shy away from difficult ideas, but he also didn't hide behind jargon. In Cosmos, he explained curved spacetime using everyday language and vivid imagery. He talked about the sun as a star that warps the space around it, creating valleys and hills in the fabric of reality. He described planets as rolling along those contours, not because they're pulled, but because that's the shape of the path itself. He made people feel the strangeness of it, the elegance of it, the rightness of it. And he did it without equations, without assuming prior knowledge, and without condescension. One of the most powerful moments in Cosmos comes when Sagan discusses the nature of scientific truth. He says, "Science is a way of thinking much more than it is a body of knowledge." And that applies directly to gravity. The shift from Newton to Einstein wasn't just about correcting errors. It was about changing the questions we ask. Newton asked, "How strong is the force of gravity?" Einstein asked, "What is the geometry of space-time?" That second question opened up entirely new domains of physics. Black holes, gravitational waves, the expansion of the universe, the possibility of wormholes and time travel. None of these make sense in Newton's framework. They only emerge when you understand gravity as geometry. And here's the kicker. Einstein's theory is almost certainly not the final word either. Just as Newton's gravity breaks down in extreme conditions, near black holes, at the Big Bang, at quantum scales, Einstein's gravity also has limit. It doesn't play well with quantum mechanics, the theory that governs the smallest scales of reality. Physicists have been trying for decades to reconcile the two into a theory of quantum gravity, but so far, no one has succeeded. String theory, loop quantum gravity, and other approaches offer possible solutions, but none are confirmed. According to physicist Lee Smolin, we know general relativity is incomplete, but we don't yet know what completes it. Sagan would have loved this. He embraced uncertainty as part of the scientific process, not a flaw. So what does all of this mean for you, standing on Earth, reading this script, experiencing what you call gravity? It means that you're not being pulled. You're not held down by invisible strings or mysterious forces. You're moving through a universe that has shape, structure, and curvature. The ground beneath your feet is pushing you off the natural path you'd follow if you were in free fall. Time itself is running slower for you than it is for someone at higher altitude. You are, in a very real sense, falling through space-time constantly every second of your life. And the only reason you don't notice is because the Earth interrupts your fall. Carl Sagan spent his career trying to give people a sense of wonder about the universe without sacrificing rigor. He wanted people to feel awe, but also to understand. He believed that science was a birthright, not a privilege reserved for experts. And gravity was one of his favorite examples because it's so familiar and yet so misunderstood. We've all experienced it. We've all dropped things, jumped, felt weight. But how many of us have stopped to ask what's really happening? Sagan wanted us to ask. He wanted us to look past the convenient metaphors and see the deeper structure beneath. Not because it's useful, though it is, but because it's true. And truth, he believed, was worth pursuing for its own sake. There's a quote from Cosmos that captures this perfectly. Sagan says, "Somewhere, something incredible is waiting to be known." Gravity is one of those incredible things. It's not a force. It's not pulling you down. It's the shape of the universe itself, telling you how to move. And once you see it that way, you realize that you've never fallen in the way you thought. You've been gliding along the curves of spacetime, tracing geodesics, dancing with geometry. The Earth isn't holding you prisoner. It's guiding your path through a universe far stranger and more beautiful than the one you were taught in school. Einstein once said, "The most incomprehensible thing about the universe is that it is comprehensible." We live in a reality governed by rules we can discover, test, and understand. Gravity, in all its geometric strangeness, is proof of that. It's not magic. It's not supernatural. It's nature revealing its deepest architecture. And that architecture is mathematics made manifest. Space-time curvature isn't just a metaphor. It's a measurable, testable, observable feature of reality. We've seen it in the bending of starlight around the sun, first observed during the solar eclipse of 1919 by Arthur Eddington. We've detected it in the orbital decay of binary pulsars, which lose energy exactly as general relativity predicts, as confirmed by Russell Hulse and Joseph Taylor. We've heard it in the gravitational waves detected by LIGO. But here's what makes this even more profound. The curvature of spacetime isn't just something that happens far away, around black holes or neutron stars. It's happening right here, right now, around you. Your body has mass, and that mass curves spacetime, however slightly. You are a participant in the geometry of the universe. Every atom in your body contributes to the shape of reality. It's an almost incomprehensibly small effect. Your mass curves spacetime far less than a planet or a star, but it's real. In principle, if you had sensitive enough instruments, you could measure the spacetime curvature caused by a single human being. Physicist Kip Thorne has noted that every object with mass or energy warps spacetime. There are no exceptions. This brings us to one of the most beautiful aspects of general relativity, its universality. The same equations that describe how the sun curves spacetime also describe how a black hole warps it so extremely that nothing can escape. The same principles that explain why you feel weight on Earth also explain why light bends around massive galaxies in a phenomenon called gravitational lensing. The same theory that predicts time dilation near Earth's surface also predicts that time essentially stops at the edge of a black hole's event horizon. There's one framework, one set of rules, and it applies everywhere. As physicist Brian Greene has written, general relativity is the language the universe uses to describe its own shape. Sagan understood that this kind of unity was deeply meaningful. It suggested that the universe wasn't arbitrary or chaotic. It had coherence, and that coherence was accessible to human mind. We didn't need divine revelation or mystical insight. We needed observation, mathematics, and the courage to follow the evidence wherever it led, even when it contradicted our intuitions. Gravity was the perfect case study. Our intuition says objects fall because something pulls them. Observation and mathematics say objects fall because spacetime is curved. Intuition is wrong. Reality wins. And that's okay. In fact, it's wonderful. It means the universe is more interesting than we imagined. Now, let's address a common question. If gravity isn't a force, why do physicists still talk about gravitational force in many contexts? The answer is that it's often a useful approximation. In the framework of general relativity, what we call gravitational force is actually the resistance to the curvature of spacetime. When you stand on the ground exerts what's called a normal force, a real force, pushing up on you, preventing you from following your natural geodesic path. That creates the sensation we call weight. In everyday language, and even in much of physics education and practice, it's convenient to treat gravity as a force because it simplifies calculations and matches our experience. But fundamentally, it's not. Fundamentally, it's geometry. This distinction becomes crucial when dealing with extreme environments. Near a black hole, for instance, talking about gravitational force becomes meaningless. The curvature of spacetime is so extreme that the usual approximations break down completely. Time slows to a crawl. Space stretches and compresses in ways that would tear apart any object, a process astrophysicists call spaghettification. These effects can't be explained by thinking of gravity as a force. They only make sense when you understand that spacetime itself is being warped beyond recognition. According to physicist Stephen Hawking, who spent much of his career studying black holes, Einstein's general theory of relativity predicted that spacetime would be curved, and black holes are the ultimate expression of that curvature. Sagan was fascinated by black holes, and he often used them to illustrate the strangeness of curved spacetime. In Cosmos, he described them as places where the normal rules seem to break down, where time and space trade roles, where the future becomes as inevitable as the past. He wasn't being poetic, he was being accurate. Inside a black hole's event horizon, the curvature of spacetime is so extreme that all paths lead inward. You can no more avoid moving toward the singularity at the center than you can avoid moving forward in time. The singularity isn't a place in space. It's a moment in your future. This is what it means for gravity to be geometry. The structure of spacetime dictates what's possible. And yet, for all its strangeness, general relativity is one of the most thoroughly tested theories in all of science. It's passed every experimental test thrown at it for over a century. The perihelion precession of Mercury, which Newton's gravity couldn't fully explain, matches Einstein's predictions exactly. The bending of light around the Sun, the gravitational redshift of light climbing out of a gravitational well, the time dilation measured by atomic clocks at different altitudes, the orbital decay of binary pulsars, the detection of gravitational waves, every single prediction has been confirmed. According to physicist Clifford Will, general relativity has been tested more precisely than almost any other physical theory. But Sagan would remind us that passing tests doesn't mean a theory is final truth. It means it's our best current description of reality. Newton's gravity passed every test available in his time, too. It took over 2 centuries before we had instruments sensitive enough to detect its limitations. The same will likely happen with general relativity. We already know it's incomplete because it doesn't incorporate quantum mechanics. Somewhere, at some scale, under some conditions we haven't yet probed, general relativity will break down. And when it does, we'll need a better theory. That's how science works. We don't arrive at truth and stop. We arrive at better and better approximations, each one revealing new layers of reality. This is why Sagan emphasized scientific literacy. Not because everyone needs to become a physicist, but because everyone deserves to understand the process of questioning, testing, revising, and improving our models of reality. The process of holding ideas tentatively, proportioning belief to evidence, and being willing to change our minds when the data demands it. Gravity is a perfect example. We thought it was a force. We were wrong. We changed our minds, and the universe became richer, stranger, and more comprehensible all at once. So here's the final thought. You have never been pulled toward the Earth. Not once in your entire life. You have been following the straightest possible path through curved spacetime, and the Earth has been in your way. Every step you take, every jump, every fall, you're navigating geometry. You're tracing geodesics through a four-dimensional manifold that we call spacetime. The ground pushes up. You feel weight. But fundamentally, you're not being pulled down. You're being prevented from falling freely through the shape of the universe. Carl Sagan would want you to sit with that for a moment. Not to feel small or insignificant, but to feel connected. Connected to the same laws that govern planets, stars, and galaxies. Connected to a universe that reveals itself through mathematics and observation. Connected to a tradition of curious humans who looked up at the sky, wondered why things fall, and didn't stop asking until they found an answer that actually made sense. Gravity isn't magic. It's not a mysterious action at a distance. It's the language of spacetime, written in curves and geodesics, telling matter how to move. And if spacetime can bend and curve, if mass and energy can warp the very fabric of reality, then what else is possible? What else are we getting wrong? What other intuitions are leading us astray? Sagan believed that these questions were worth asking, not to undermine confidence in science, but to celebrate it. Science thrives on being wrong and then correcting itself. It thrives on discovering that reality is stranger than we thought. Every time we overturn an old model, we don't lose understanding, we gain it. We see deeper. We see clearer. So the next time you drop something and watch it fall, remember, it's not being pulled. It's following spacetime. The next time you feel your weight pressing down, remember, you're being accelerated upward by the ground beneath you, held away from your natural freefall path. The next time you check your GPS, remember, satellites orbiting overhead experience time differently than you do because they're at a different position in the curved spacetime around Earth. These aren't abstract ideas. They're descriptions of reality. They're the universe showing you its true face. School taught you gravity wrong, not out of malice but out of simplicity. Newton's gravity is easier to teach, easier to calculate with, and good enough for most purposes. But it's not the whole story. Einstein gave us the whole story, or at least a much bigger piece of it. And Carl Sagan spent his life trying to make sure that story reached everyone, not just physicists. Because understanding gravity, really understanding it, changes how you see everything. If space can bend, if time can slow, if the universe has geometry that we can map and measure and predict, then what else is waiting to be discovered? What other truths are hiding in plain sight, waiting for someone curious enough to ask the right question? Somewhere, something incredible is waiting to be known. And gravity was just the beginning.